10.0.0/16. So basically, routers on that side will use the left 16 bits of this any given IP address to route the traffic. Once the traffic arrives at a router R1 in hub, now we have two internal subnets. And to create two subnets, basically bit number 17 was borrowed to create two subnets. This router needs to store two entries, and this router is going to identify these destinations based by comparing 17 bits, right? We already discussed this yesterday. Let's say the destination is a node in this network. Once a packet arrives at R2, checking the first 17 bits is not enough because each of these networks have the same value in first 17 bits. R2 will use the first 19 bits to differentiate between each of these networks. And this is sort of how routing is done, right? Now, what is supernetting? Supernetting allows routers to combine multiple networks. For R2, there are 4 subnets, but R1 does not need to know the address of each of them. It will combine these 4 subnets, and rather than using /19 notation, it will combine them into one big network with /17 notation. Similarly, a router on this side will not keep these two network IDs in its forwarding table. It will keep only one entry with /16 notation. Now we are going to learn how to combine multiple subnets into one supernet. These slides are already uploaded. And for teaching this concept, I will use a tutorial that is already uploaded on Moodle. This is the intro that I was giving already, so I will directly jump in. So consider this network. We see many routers, obviously many different networks. You can see the network IDs over here. 192.168.1.240.244.248. And here the subnetting has been done based on this line, right? As we go towards the internal parts of the network, in this part of the network, different subnetting is being used. Now, imagine we do not do any supernetting, we don't combine anything, then the production router will have to keep all these network IDs in its table. It needs to keep a path to 192.168.1.224, which is /28. Can you find the network ending with /28? Where is it?
It's on the left.
Left. Here, right? It needs to keep a path for this network 192.168.1.240/30, this one, .244, this one. So the point here is it needs to keep multiple paths, right? Same is the case for sales. By applying the concept of supernetting, which we are going to learn right now, the production router will have to keep this entry 192.168.1.0. If you see, for all these networks, the first 24 bits are 192.168.1, right? And you will see how to do subnetting now. And what is the advantage of subnetting? We can clearly see it reduces the size of routing tables, as a router has to keep only a few network IDs. It provides a better overview of a network for the router. You don't need to go into multiple subnets and everything. And obviously, it decreases the use of resources such as a router's memory and CPU. Memory because lesser entries are stored. CPU because the router does not have to search through a lot of different entries. And it obviously decreases the time required to rebuild routing tables if there is any change. We will use this example to learn how to supernet a network. Okay. How many routers do you see in this example?
4.
4, right? Please also focus on these interface numbers. We may need to consider them, right? So without supernetting, without route summarization, all of these routers will have to keep all these entries. So at R1, you can see all these routing entries. R2 has the biggest table. It is keeping all these network IDs in its routing table along with their subnet mask and exit. For instance, R1 is saying this network 100.0, which is basically this one, is reachable via interface G1, this one. Similarly, the next network, which is this one, is reachable also via G1, 102.0. Are these network IDs consecutive to each other? 100, 101, 102, 103. If we look at the third octet, they are, right? We know this from our lecture yesterday. So what we are going to do, we are going to supernet these subnets into one network ID. Similarly, R1 is going to supernet these networks as well. In this direction, obviously, there is only one network. So you cannot apply the concept of supernetting. It makes no sense. Okay. So supernetting is very easy. And we are going to start by supernetting these networks on R1. Okay. So what is step 1? Step 1 is arrange the network addresses in the ascending order. Okay. So these are the 4 networks on the left to which R1 is connected directly. Write them down, but write them down in the increasing order. So 192, same value. 168, same value in the second octet. In the third octet, based on third octet, we will arrange them in the increasing order, right? Next, step 1, expand the addresses where the first difference occurs. Let me zoom this part. Okay. So is the change occurring in the first octet? Here. No.
No.
Is it occurring in the second octet?
No.
It starts in the third one. So expand the addresses where the first difference occurs. It occurs in the third octet. So we will change only these values to binary. You can change everything to binary, but that will take a long time. No need of doing it, right? Second step, determine where the change first occurs. So no change here, no change here. And now start comparing the binary numbers. No change here, all ones, all ones, all zeros, and the change occurs here basically. All ones here, and on the right side I can see 0, 0, 1, 1. So just like the network mask, you are going to draw a boundary here. Okay. What will we do next? 0 the bits to the right of the line. So whatever you see on the right of the line, set everything to 0, like we did for the host bits, same logic. Done, right? Everything is transformed to 0. Next step, change the subnet mask to the new location. Till now, the subnet mask was of length 24. This boundary is at position 22, basically 8 bits, plus 8 bits, 16, plus 6 more bits, 22, right? So now we will reduce the subnet mask from 24 to 22, right? Translate back to the dotted decimal. So change these numbers back to the dotted decimal form. Do you see any difference over here? Are all of them the same values?
Yes.
Yes.
They are, right? So rather than saving 4 of these entries, we have supernetted these 4 networks into one network of /22 length. This is your solution. Okay, so what is R1 going to do? It is not going to
Professor,
just give me 1 second, please. So rather than storing the network IDs and paths to these 4 networks, R1 is going to store only one entry. Okay, no, sorry. R1 is going to store all these entries because they are directly connected over here. Okay, R1 is going to announce that supernetted single entry to R2 and others. Okay, so R2 will receive only one entry, 192.168 dot number slash 22, and R2 will be able to reach all of them by only one entry. Yes, please.
Professor, the step 4 and step 5, can you explain one more time?
Yes, please. Sure. So what did we do in step? Step 3 is clear, right? We set all the host bits to 0.
Yes, Professor.
Okay. So in step 4, as the boundary is not 2024, the first change occurs after 22 bits. We will reduce the subnet mask from 24 to 22. And how did I come up with this number? I have to compute the number of bits to the left of this boundary. And I see 8 bits plus 8 bits plus 6 bits in this third octet are exactly the same. Clear?
Yes, Professor.
Okay. And next step is simply convert these numbers back to decimal. And then this is your solution. By the way, this step is done just to explain what is happening. Okay, you don't need to convert them back. They are the same. You need to just convert one back, like in the simplest way. And this is your supernetted network. We are going to apply the same concept on the other routers now. R3. Okay, so R3 is basically connected to 4 of these networks. The network IDs are different. Same logic. Expand the address where the first change occurs. We can see the first change occurs in octet 3. Convert these values to binary format, only the values in the third octet. Find the boundary where the change starts. You can see the change starts here, right? Take your time. The first change occurs here, right? Same logic. Set all the bits on the right side of the boundary to 0. Reduce the subnet length from 24 in our example to 19. Once again, why 19? 8 bits, not changed. 8 bits, same, 16. And then bits 17, 18, and 19 are also the same. Okay. We have supernetted these 4 networks into one. And the supernetted network ID is only 192.168.96.0. R3 will share this supernetted ID with other routers, and they are going to store this only one value. What I have done, I have added some exercises for you guys. This file is already uploaded. Okay, so my recommendation is, let's say you have 2 networks in front of you, supernet them. Once you get your answer, compare your answer with the given answer over here. Okay, so a couple of exercises are solved and a few are not solved. I will go through a few of these. Be very careful. We are going to see in the slides in a couple of minutes. If I give you some subnets, even if they look similar, it is not necessary you can always supernet them. Okay, so there are some conditions under which supernetting can be applied. We need to understand them clearly. So more on them in a couple of minutes. So in this example, these are the first 2 octets. We are not supposed to convert them to binary, but I just did it for the sake of understanding. Can you show me where is the exact boundary? Give me the bit number on which the first change occurs in the third octet. Start from here, 17. Can someone tell me the last bit after which the change occurs?
23.
23, yeah, 23 is the one in which the change occurs. So the last unaffected bit is 22. You will draw the boundary here, okay? And you know the rest. We will set all these bits to 0. Reduce the subnet mask to which value? Slash 22 or 23?
23.
Wait, I made a mistake while drawing. Seventeen, 18, 19, 20, 21, 22. Yes, right. 22, not 23, because the 22 bits on the left are same in all these 4 networks. 23rd is different, right? So we will
No.
reduce. Yes, please.
So, doctor, so when we draw the line, it's until the last bit that is not converted. The other side will be the bits that are converted, right?
Yes, on the left side, bits bits are same, if I understand your question correctly, and the first change occurs on the right side of this line, right?
Yes.
So whatever is on the right side of this line will be set to 0.
Thank you, doctor.
Yeah. So I have added different exercises for you. Take your time and go through them. Okay.
Professor,
Yes, please.
all of them are the same idea?
Same idea. They're different examples.
Okay.
Okay. Or let's go through one more example and it will be an interactive exercise. You will answer. You mean like any of you will answer. Let us subnet these networks. So already I have converted these binary numbers, these IP addresses to decimal format. And for these networks, /25 is the subnet. Where will the first change occur? This is a bit tricky. Wait. Give me the bit number, the last bit which is the same. Starting from left.
It's bit 22.
22, so let's see, 17, 18, 19, 20. How about 21? Can we reduce further? 22 is here, right?
Yes,
Yes.
doctor.
Can we reduce to 21?
No,
No, why not?
they are the same.
They are the same. So 21, correct. Oh, wait, did I make a mistake here? Let me check. 1, 17, 18, 19, 20, 21, 22. The first 22 bits are identical, right? Unless I made a mistake. Wait, 17, 18, 19, 20, 21. Yeah. This is 22. I will correct it and upload it again, okay? So the point is find the boundary, set everything on the right side to 0, reduce the subnet length accordingly, and you need only one address. So for this network, okay, this is the network ID. I think this is using the incorrect example value. We can go back to this one. So for this network, we had reduced the length from 24 to 22. And this was our new network ID. How will you obtain your new network ID? We will consider only the left 22 bits. Everything from 23 third and onwards bit will be set to 0. How will you find the broadcast ID? Just for the sake of practicing, if required, you set all the host bits to 1 and you can get the broadcast ID of any given network. That's it.
So, Doctor,
Yes, please.
in the quiz, if you give us a question about supernetting for IP addresses, what should be the answer? Only one IP address, which is the network ID, or the broadcast?
You will be able to answer your own question in 5 minutes. So give me 5 minutes. Maybe the final answer will be only one network. It could be 2 networks, or there may be no change at all. You may say supernetting cannot be applied.
Okay.
Okay, so thanks for the timely question. I will answer your question from these slides. So I shifted to that document on this slide. Students must study the tutorial on supernetting discussed in the class, so download it. Okay. Disclaimer, not all networks can be supernetted. So what are the conditions? Supernetting requires the set of IP ranges must be contiguous. They must be adjacent to each other. Right? You will see the meaning on the next slide. All the networks that you are combining together must have the same subnet mask. We saw /24, /24, /24, /24. If the subnet masks are different, you cannot apply supernet. Moreover, those networks should belong to the same class of networks, class A, B, and C that we discussed yesterday. If any of these conditions are not met, the networks can not be supernetted. Let me show you some examples. Okay. I have given you 4 different networks here. Do they look similar?
Yes.
They are. Can you draw the boundary where the first change starts?
Yes. It's uh.
Here, if you
It's on 21. 21.
yes.
21th bit.
Yes, Mariam,
13.
thank you. 21 bits, right? So apparently it seems we should supernet these 4 networks into only one network, and we should reduce the subnet mask from 24 to 21, right? But we have a problem. The problem is these 4 networks are not consecutive. Check this one, 192.168.1.0 /24. What do you see next? 3.0 /24, 2.0 is missing. 4.0 is also missing, right? The binary values of the third octet are not contiguous. No common prefixes exist for all these networks, right? So if some of these networks are missing, you cannot supernet them. Okay, I will share some online resources with you, an online calculator that will help you sort of play with different numbers and see if supernetting can be applied or not. That will reinforce your concepts. Second rule, you can supernet multiple networks only if they have the same subnet mask, meaning their prefix length is also the same. Check these 4 networks. First, the IP addresses. Do they look similar? Yes, they do, right? The first change occurs in the third octet, and these numbers are consecutive, 0, 1, 2, 3, okay? Unfortunately, we cannot supernet them into one. The problem is these subnet masks have different lengths. So even though everything else is fine, the network administrator who has done subnetting has used different subnet masks based on his or her needs, right? So subnet masks are different, you cannot supernet them easily. Last, and I think this is easy, even if I don't put this rule, you guys will not make a mistake. You can only supernet networks that are part of the same class. Quite clearly, even if I don't put class A, B, or C, these IP addresses look starkly different, right? You cannot supernet them. I repeat, if you are given networks that belong to different classes, they cannot be supernetted into one. Clear?
Yes, doctor.
After these two slides, we are going to discuss routing algorithms. What is a routing algorithm? A routing algorithm is one that enables every router in a network to discover other routers and then compute shortest paths to them, right? So once a routing table computes routes to all known destinations, it adds them in a table, okay? And that table is called data forwarding table here. In this example, I can see a router is not storing obviously all the destinations, but rather it has stored a range of destinations. A router will receive a packet, an IPv4 packet. In that IPv4 packet, it will inspect the header fields, right? In the header fields, it will check only the destination IP. Okay? Whenever a host generates a packet, it adds the source side IP address and the destination IP address, right? So imagine a router is connected to multiple networks and it has received a packet from this side. It is going to inspect the destination IP field, okay? And then it is going to find the best match in its routing table to decide whether to forward that packet through interface number 0, 1, 2, or maybe there is another interface 3, right? So check this part. When a router receives a packet, it matches the destination IP address with what? The longest prefix match in its routing table. So basically, routers, switches, they don't use dotted decimal notation. Obviously, machines understand binary numbers, zeros and ones, right? So imagine a router, let's say R1, is connected to 4 interfaces like this diagram, and it has a forwarding table. In one of the entries, it has entered this. So if it receives any packet in which the destination IP belongs to this range, the router will forward that packet to interface 0. If it receives a packet in which the IP belongs to an address in this range, that packet will be sent to interface 1 and so on, right? What is a by default interface? If a router receives a packet and it cannot find any best match in these 3 rows, this is the default gateway. Okay, so it is like a default gateway at your home. At your home, your default gateway is your internet box because it connects you to the ISP, right? Same logic here. Let's do some exercises. In the last slide, I used the term longest prefix match. So when looking for a forwarding table entry for a given destination address, this approach says the router is going to use the longest address prefix that matches the destination ID. Okay, so some examples here. Let's say a router has received a packet in which this is the destination IP address in binary. A router is going to find the longest match in these entries. Please check these three rows. Is there any difference in the value of the first octet?
No.
They are exactly the same. So the router cannot decide by inspecting only these values. Now inspect the 9th bit. Same. 10th. Same. Same. Right. Keep on going. 11th. Same. So apparently you can see all these numbers are same, right? Till which point? These numbers are exactly the same till this point, at least, right? The first change occurs over here. Okay, so this is bit number 17, 18, 19. The first 20 bits are exactly the same. And the first change occurs here. Can you give me the longest match of this IP address with any of these?
Sorry, doctor, I did not understand the question.
Okay, let me put it in a different way. First, are these first 20 bits on the left exactly the same in all these three interfaces?
Yes.
Yes. So let's now inspect bit number 21. What is the value here?
0, and then the
0.
second
And
one is
now
1.
let's check bit 21 here. I have 3 entries. These 2 entries are 1, so obviously interface 1 and 2 is not the right choice. Do you see a 0 here?
Yes.
So out of all these possibilities, this destination IP address has the best match or longest prefix match with this entry, meaning the router is going to forward that packet on interface number 0. Okay. Let us try another example now. This one. The first change occurs at this point. What do you guys think? Which interface will be selected to forward this second packet?
Interface 1
Why interface 1?
and interface 2.
Okay. Can interface 0 be selected?
With the second line,
Yeah,
no,
with the
it
second
cannot
line. No,
because
because
it's 1 1
here I see 1 and here I see a 0. So this is
0.
cancelled,
Yeah.
right? Now we will come. We have these candidates. Okay. Is interface 3 a candidate, by the way?
No, because it's
No.
everything other than what we
Yeah,
have.
exactly. Because at least something is already matching, right? If you receive a number 0, 1, something, then obviously none of the bits will match and we will forward that packet on interface 3, right? So, okay, so only 1 and 2 are options. This is same, sorry. Here I see 1, here I see 1. And then what do these stars mean? Stars mean, asterisks mean doesn't matter, right? So whatever the value here, 0 or 1, forward it on 2. But here we don't have asterisks, we have specific numbers. Do these 3 next bits match to this sequence?
Yes.
I'm talking about the second IP.
Yes.
They are the same, right?
Yes.
So 3 zeros followed by 2 ones followed by 3 zeros. And then the remaining sequence does not matter. So we have found a longest prefix match, and our longest prefix match is the second entry, meaning the router will forward the second packet on interface number 1. Okay.
Does
Clear?
doesn't interface 2 also match?
No, it matches, but it matches till this point. I agree with you. It matches, but it matches till bit number 21.
Yeah.
Okay. And then for bit 20 to 23, for interface 2, the rule is if there is a 0 or 1 doesn't matter, right? But interface 1 has more bits and they are specific. 0, 0, 0. We will check. Do you see a 0 here? Yes. A 0 here?
No.
Yes. A 0 here? Yes. So interface 2 is better. I can give you one example. Counter example. What if the destination IP is
It will be interface 2.
Yeah.
interface 2? Yes. Because interface 1 says we should have zeros here, and interface 2 says any of zeros and ones, right? So interface 2. Correct answer. Thank you. Okay. And this is how routers forward any given packet. They just look at the destination IP, find the longest prefix match, and forward the packet. If there is no match, then a default interface is used to forward them. In case you want to explore more about subnetting, even supernetting, go through these slides. I have attached them as sort of extra resources for practicing and learning shortcuts. So please go through them. We have already covered enough exercises in the book, right? So that's the end of this part. And now we will go to the next one. I use these slides in another course, so this will be chapter 0 and part 3. Chapter 7, part 3. We are still in the network layer services chapter. Okay. And now we are going to learn dynamic routing protocols, or first, what is meant by routing, its difference, like its comparison with forwarding, and then we will discuss some routing protocols. This chapter maps to chapter number 5 of the textbook. Here I am following numbering as per the series or sequence of our topics in the course. Actually, you will find these details in chapter 5 of the book. Okay. So in this part of the lecture, we are going to discuss two categories of protocols: link state routing and distance vector routing. Okay. We will cover this one first. What is a routing protocol before we go into details? So here we have seen this example many times. So imagine a client in this part of the network at CUD, let's say, wants to connect to Google server, which is placed in another part of the world over here, right? So obviously, or this could be your home network, that is better. At your home, your machine will generate a packet. It will contain the source IP, the destination IP, and then the machine is going to forward that packet to its default gateway, which is your internet box at home, right? What is the goal of a router? A router connects different networks. We already know that. So routers have algorithms called routing algorithms that enable them to discover other routers in the network, compute shortest paths to them, so that these routers can send traffic to any reachable destination within a network, right? So in this example, where we can clearly see this, a packet generated from this machine will pass through a series of routers. The question is, how do these routers compute best paths to any destination? Okay, this is because of a routing protocol. Okay. So a routing protocol is nothing but an algorithm, a series of instructions that enables routers to discover other routers within the same network, maybe different networks, depends on the scenario, and then compute shortest paths to them. What is a path? So once a router knows shortest path from source to a destination, in this case, follow the red line, please. A path is a sequence of routers packets traverse from given initial source to the final destination. How will you define the best path? Depends on the metric. Some algorithms say best path is the one in which the number of links is minimum. So let's say they will consider this as one jump, link 2, link 3, link 4, link 5. Okay. Quite possible this link, if you look at here, has a capacity of only 100 kilobits per second, whereas there is another path from this direction that has a capacity of 1 gigabit per second here, 1 gigabits per second here. So some algorithms say best path is one that is shortest in terms of hop count. Other algorithms say best path is one that offers the best throughput. Okay, minimum maximum bottleneck value depends. We will not go into these details. By the way, designing most efficient routing algorithms has been a big challenge, and it has been a focus of research for the networks related community for the past 20 years. Before we go to dynamic routing, I will first quickly focus on static routing. We had a lab on static routing a few weeks ago. Okay, so consider this network. We have three routers A, B, and C. These are the interfaces, right? One option, if your network is small, you don't necessarily have to configure a dynamic routing protocol on the routers. You can hard code addresses. You can say on router A, any destination within this network is reachable via this interface. So now if a router A receives any packet that belongs to a network over here, it will directly forward that packet to the concerned interface, this one. Right? The problem is, what if there are new routes in the network? There is a new router that can provide a much better and much faster path to the same destination. With static routing, you have to manually delete old path, add new route, and then add changes. Okay, so static routing is not good for medium to obviously bigger size networks. Okay, because they don't have any fault tolerance. Let's say you are using this path. If this link goes down, you will not be able to reach those destinations, even though you have an alternate path, because you were using hard-coded static routing. So what's the solution? The solution is to use dynamic routing. Okay. Dynamic routing protocols allow routers to automatically learn updated routes, even broken links if there are any. Okay. What is the advantage of dynamic routing? Adaptability. Routers automatically adjust to changes in network topology. They are scalable. We can dynamic routing can handle large networks and frequent updates if there are any. If you add a new router, that router and others will discover each other within a few seconds. They will compute new forwarding tables, and they will start forwarding data for others. And obviously, it adds fault tolerance. So let's assume this is the structure currently, and this link goes down. The moment this link goes down, R3 will detect there is a problem in this area. R2 will detect this network is no longer reachable. They will start, let's say R2 will start sending traffic to R3 via this path. Okay, and they will also inform other routers that there is a change. I will first focus on this example. So assume R2 has learned about a new network, that it is connected to 167.16.3.0/24. Okay. What it is going to do, it is going to generate routing updates. It will announce a packet saying, I have a route to this network, okay, using whatever metric it is using, hop count, throughput, whatever. It will do the same on this link. Through this packet, R3 will discover this network is reachable via this interface. Through this update, R1 will also discover that this particular network is reachable via this interface. They are going to add this new entry in their routing table. You can see it here. 172.163.16.3.0 for R1 is reachable on this interface, and the next hop to reach their destination is this IP address. Is this part clear?
Yes,
Um,
doctor.
Thank you. Yeah. So quickly, the difference between routing and forwarding. Routing is calculating routes to be taken, to be taken by packets from source to destination. Okay, so routers run a routing algorithm, discover best possible paths, and this process is called routing. Okay, what is forwarding? Once the routing algorithm converges, every router will add entries in its forwarding table. It will add reachable IP addresses in one column, next hop IP address in another column, cost to reach that network, it could be a number of hops, and that is called a forwarding table, a routing or forwarding table. Once a forwarding table has been computed, I showed you one earlier, the router will receive packets from some source, simply inspect the destination IP field, choose the most appropriate next hop IP or next link and forward that packet. Based on which rule? I repeat, forwarding is simply receiving a packet, checking the destination IP, applying the longest prefix match strategy, and sending the packet or forwarding the packet on the correct interface. That's it. Okay. Which one happens first? Routing or forwarding? What do you guys think?
Routing.
Routing. First, you need to know the paths, and only then can you forward those packets. Thank you. So this is just a visual depiction of the same scenario. Okay. So every router in a network, okay, it runs a routing algorithm to discover shortest paths. At the end, it computes its forwarding table and then stores them in its memory. Then forwarding is simply receiving a packet, checking the destination IP, applying the longest prefix match over here, and forwarding the packet on the most suitable next link. That's it. Okay. I think the difference is clear, right? So I will not repeat the same thing in this example. So what we are going to do now, we are going to learn two different routing algorithms. They belong to two different categories, rather I would say, we will learn two different types of routing algorithms: link state routing and distance vector routing. First, I would like to describe how is a network represented, right? So a network is represented as a weighted graph. In this graph, we have a set of nodes. So basically every node is representing a router. Y is a router, X is a router, U is a router. And then we have a set of edges. Okay. So in this example, our N, which is a set of routers, has these components: node U, V, W, X, Y, Z. And then E is the set of edges in this graph. Okay. E is the set of links basically. Are U and V directly connected? Are they direct neighbors? They are, right?
Yes.
So in this graph, we will add an edge from U to V. And in the next slides, we will see we also need to store the weight. So we will add an edge UV and we will also store this value, cost. Similarly, we will add an edge UW. Okay. Did I miss?
Force one.
Is it missing?
Force one. No, force one.
1, 2, 3. No, it's VW. I was looking for UW. Okay, UW is missing. I will update these slides.
Oh.
Okay. I can consider another. WZ. Do you see WZ? Yes, I do. Okay. So as there is a link between them, we will add an entry in the set of edges and we will also store the cost. By C subscript AB, we will represent the cost of a direct link connecting A and B. For instance, in this example, we can say cost to reach Z from W, cost to reach Z from neighbor W is equal to 5. One question, are U and Z neighbors? Is there a direct link between them? No. So we will set cost from U to Z equal to infinity. Infinity, very high value, right? Costs are defined by the network operator. Okay. They can always be 1. If a protocol counts only the number of jumps, then the cost of every link will be 1 by default. Okay. But most of the protocols, they use different metrics. We can say this is the delay. Okay. So what is better, a smaller delay or higher delay? Smaller. So let's say you want to send a packet from X to W. You have two options. You can either send it directly to W and there will be a delay of 3 units, or you can send it to via V, which is not good because the total delay will be 2 plus 3, 5, which is greater than this value. Can you give me the best path in this diagram?
X, Y,
smallest-
W.
Perfect. So X can give packet to Y and Y will forward the packet to W. So the total cost will be 2. A routing algorithm does nothing but enables a router to discover others and compute these best paths. Okay. I will rather come back to this diagram at the end. I will explain everything from the examples while describing algorithms, and we can discuss this summary at the end. So we have two different classes of algorithms, link state and distance vector. I will start first with the link state algorithms. Remember one thing, they are scalable, meaning as you increase or reduce the size of the network by adding or removing routers, they are very scalable. Plus, the convergence of a routing protocol in a network is very fast with link state routing. By the end of this lecture, you will know why. So what is link state routing? Link state routing is a technique of dynamic routing where each of these routers builds a complete map of the network topology, meaning once every router shares its link state with everyone else, at the end, Z, W, X, Y, everyone will be able to constitute this graph. I repeat. Once every router informs about its link states, the other routers, every router will have the same view of the topology. You can say it this way, every router will know this graph, right? The question is, what is a link state? A link state is, consider this node. This is router U. How many nodes is it connected to?
3.
3. It has, or we will say it has 3 links. Okay. It has a link with W with a cost of 5. It has a link with V with a cost of 2. And it has a link with X with a cost of 1. A link state update is basically a packet, a small packet in which you will generate a packet. It will say, I am U, I'm source U. I have a link with node V, and V is reachable at a cost of, I can reach X. I have a neighbor X at a cost of 1, and I have a neighbor W reachable at a cost of 5. Okay. Consider this as a link state update, and you will generate this small packet and send it to everyone. How will it send it to everyone? Basically, it will flood the packet. V will receive it. X will receive it. W will receive it. W is going to add some entries in its table. W will say, okay, apparently there is a node U, which is already my neighbor. U has a neighbor X, okay, reachable at a cost of 1. So W is going to add all these details. Okay, we are not going in this part because we don't need that much detail, right? So W will update this entry of link state. W will say, okay, now I know there is a node U in the network and it has these 3 neighbors and their costs. W is going to forward the same packet to all other links. So basically, at the end, every node in the network will receive this update. This will be done by everyone. Y is also a router. It will generate its link state, which is basically a small packet saying, I am source Y. I have a neighbor X, reachable at a cost of 1. I have another neighbor Z, reachable at a cost of 2. W, reachable at a cost of 1. Did I miss anything else? No, only 3. This is a link state update packet. Y will flood it to everyone. So its neighbors will receive it. They will update their entries and they will forward those packets to everyone. I think you can easily imagine, once everyone has shared their link state updates with everyone else, they will be able to constitute this graph. So assume everyone has this graph. And now our computation starts. Once everyone has this graph, every router is going to compute shortest paths towards the destination. So till now, I described link state advertisements. So the advertising these link states messages is called LSA. Every router will have this topology database. And now we will focus on the path calculation aspect. To compute shortest paths from any source node to all other destinations, this algorithm is used. Have you guys studied it in discrete maths? It's called Dijkstra or Dijkstra. Some people call it Dijkstra, depends on the pronunciation. Did you guys study this algorithm in discrete maths? It's not required. Okay. So this algorithm is centralized. Okay. Every node knows the network topology, the complete graph. Okay. And every node will know the link cost to all nodes. How does every node knows the link cost, who is available in this network and their neighbors? Through link state advertisements that we discussed earlier. Once this algorithm completes its cycle, you will get a table containing shortest paths from one source node to all other destinations. So basically, at the end, it will give us a forwarding table at one node. Which particular node? The source node that we are going to select in the beginning. And it is iterative in nature. We will see how. Some notations before we go into details. By CXY, we already saw this earlier, we represent the direct link cost from X to Y. So if X and Y are neighbors, their cost could be 1 or 2. In case X and Y are not direct neighbors, then we will set that cost to infinity. By DV, we represent the current estimate of cost to reach node V from the starting node U. Okay, I will prefer to explain this from this example. What is CVW? Are V and W direct neighbors? Yes. So CVW is equal to 3. Are V and Y neighbors? No. So CVY will be infinity. What is, imagine, and we are going to use the same example. We are going to start running this algorithm and we will choose U to be the starting node. Okay. Let's say we have already found the cost to reach V from U, the current shortest possible cost. Okay, it's not probably the best one. So we will add dV. What is dV in the first step? dV will be cost to reach V is 2. And if we send a packet from U to V, who is the last router before V? Okay, the last router before V on this path is U itself because they are direct neighbors. Okay. What is PV? P is basically the predecessor. So what is the best cost to reach V from U? Till this step, the best cost is 2, which is VV, and PV is the predecessor of V. The predecessor node just before V on the path from the starting node is U itself. So we will say U. Okay. So I hope this is clear. It will be clarified further when I start solving this example. Okay. So the algorithm has 2 phases. First, the initialization phase. So you will be given a topology and you have to select any of the nodes as the starting point. So initially, you have 2 sets. N, which is the set of all the nodes. We saw it earlier. And now we have another set, N prime, which will initially be empty. In the first step, we are going to choose the starting node, let's say U. And we are going to add U as the first node to N prime. So, okay. So initialization requires you to pick a starting node and add it to N prime. Next step of initialization. For all nodes V belonging to this graph, if V is adjacent to U, meaning if any of, you will go through all of these nodes one by one. If any of those nodes is a direct neighbor of U, what will you do? You will update D of V. Quickly, are U and V neighbors? They are. So we are going to populate. So here you can see V, W, X, Y, Z, all of the nodes. We are going to populate this. We can reach destination V at a cost of U, at a cost of 2, and the predecessor node will be U itself. We can also reach W because they are direct neighbors. The cost to reach W from starting node U is 5. and the predecessor along this path is u itself. Same case for x. Cost to reach 1, predecessor 1. Initialization is done. Okay, now one part is left. If there are other nodes that cannot be reached, set their dv cost to infinity. Can we directly reach y from the starting node? No, they are not neighbors, so infinity. Cost to reach z, infinity. Now the second step, which is the actual calculation, involves a loop. This is an iterative algorithm. What will we do? Find a node not in n prime. So find a node that is not already part of this n prime set. And the cost to reach that node is minimum. So from now onwards, I will use this slide. This is the loop part. Can you find a node to which the cost to reach is minimum in this row? V is reachable at a cost of 2, W at a cost of 5, X at a cost of 1. Is it X? Hello, am I audible? Hello.
Yes, Professor.
Okay, thank you. So apparently out of all these 3 nodes, the cost to reach X is minimal, 1. Is X already part of n prime? No, it is not here, right? So what we are going to do, find a node not in n prime such that the cost to reach that node is minimum. So we just chose X, step 1. Add X part of n prime. Next, the main part of this algorithm. Update path to all nodes considering X. In short, what we mean is in step 0, we only added paths that were directly reachable from the starting node. Now we have added X. Okay. In step 1, we are seeing what are the best paths that can be reached from U, considering X is already part of the shortest tree. Okay, if you see, we have a bold red line here, right? Okay, can you reach V through X? Can you reach V, the same node, by this path?
Yes.
What will be the total cost? 1 plus
2.
2, 3, which was 3.
3.
Is there already a path between U and V that we added earlier? Yes.
Yes, and it's
What is
shorter.
better? Is a cost of 3 better or a cost of 2 better?
2.
2. Okay, so basically to describe this scenario, we have this link. We are computing cost to V in step 1, which is minimum of what? Currently discovered cost to V. So currently discovered cost to V was 2. Okay. We just added X, right? So we are going to consider this cost as well. Cost from U to X, which is here. So cost from U to X is 1. What is current cost to reach X?
Can you repeat, Professor? I didn't hear you.
Okay. What is current cost to reach X from U?
1.
1. Oh, wait, I may have made a mistake here. Wait. I think I have an animation. Okay. So consider this line. From U, the current cost to reach V is 2, right? So this is what we got. From U, the cost to reach the currently chosen node over here, which is X, so our A will be equal to X, is 1. Got it from here. And now through X, I can reach this node V. The cost over here is 2. I will mention this one. Okay. So what is the minimum of 2 and 3? It is 2. Okay. Till now, we had said from U, the best path to reach V is directly. How do I know directly? Because we entered V can be reached at a cost of 2. And the predecessor to reach V from U will be U itself, meaning you will directly give it back into V. Okay, you will see differences for other nodes briefly. DW from U, W was already reachable at a cost of 5, so we will 5 here. We just added X, so from U we can reach X at a cost of 1.
Plus
And
3 is
from
4.
X, we can also reach W, right? So 1 is 3. 5 versus 4, which cost is better?
From X.
From X, perfect. So till now we had said U will W was reachable at a cost of 5 and U was the predecessor, meaning it was supposed to give packets directly to W. We just found a better path from U to W through X, right? So we are going to update this entry here. We are going to improve the table. We will say W is now reachable at a cost of 4. And the predecessor to reach W from U on this path is X. Okay. So cost is 4, 1 plus 3, 4. And the predecessor before W will be X. Same thing for Y. Till now, Y was reachable, not reachable, infinity. Infinity. Through X, it can be reached at a cost of 2. 1 plus 1, 2. 2 is smaller than infinity, so we will update this entry. So Y is now reachable at a cost of 2, and the predecessor to reach Y from X will be, from U will be X itself. And I think you know the rest. We will keep on repeating the same process. Now, same repetition again. Go through these nodes. What is the smallest value?
2.
2. We have a tie, by the way. So we can either add V or Y to our set, either of the two, as long as they are not in this set, right? So loop around, we will see what did we add here. Y. By chance in this example. So Y has just been added to this set, and after adding it, we will add this path, meaning we have found the least cost paths from U till these nodes, right? Okay. Exactly repeat the same thing. What is the current cost to reach V from U? It is 2.
Professor, I have a question.
Yes, please.
For the UX to V, isn't it 3?
UX to
V.
it is 3, yes.
But in the second column it's 2. 2 slash
Yes.
2 comma U.
Yes, because we are trying to find the best paths. Let me do this calculation. When we added X in the last step,
Okay.
okay, we said, okay, till now, the best path to reach V had a cost 2.
Yeah, from U to
And the
V.
predecessor was U, right?
Yeah.
Now through X, we just found a new path. From U to X, we can reach at a cost of 1. From X to V, we have a link by chance here.
Uh-huh.
So we will add 2, right?
Yes.
So we have to choose a minimum of 2 and 3. Which is better, 2 or 3?
Oh, okay. Okay, I see.
So 2 is better, we did not modify it.
Okay, I get
But
it.
in case of W, so
We had to modify it because 4 is less than 5. Okay, got it.
exactly, we found a better path, right?
Okay, thank you.
Actually, not the difficult. The rest is a repetition of the same steps. We just added Y, and we will check through Y, can we find a better path to reach any of the destinations? Remember one thing, the starting node is always the same, okay? So simply this way. Should I check this link? No, it is already on the best path, right? It is marked red. So from Y, I can reach only 2 destinations, W and Z. So I will check only for them. What is current cost to reach W? 4. What will be the cost if we reach W on this path? Current cost to reach Y is 2. We are just reading this number. And Y to W cost is 1. I will simply add that. What is min of 4 and 3? 3. So we just found a better path to reach W. From the starting node, we are going to update W column. What should I write here?
3Y.
3. And the predecessor to reach W will now be Y. Perfect. Okay. And this is how we will proceed. We are not going to modify that cost. No changes there. One change here, and there is another change. We can reach Z from Y. Till now, the cost to reach Y was infinity, meaning Z was unreachable. We can reach Y at a cost of 2. And Y to Z cost is 2. So 2 plus 2, 4. As 4 is less than infinity, let's update this path. 4. And the predecessor of to reach Z will be Y itself. Let's say. Okay. Who is the next candidate? I think we are done with this now. For the next step, should I select V, W, or Z?
V.
V. Is V already part of N prime?
No.
No. So very easy choice. V. Look at the neighbors of V. They are U, W, X. Will there be any changes?
I don't know.
No. Don't worry. I have some examples for you guys. Solve them at home. Okay. So first we are considering W. Through V, we can reach W at a cost of 5 because this is the best cost too. Plus 3, 5. And our table says the current best cost to reach W is 3. So we don't need to change anything because 3 is already the best path. From V, we can reach X. So the total cost will become 2 plus 2, 4, which is obviously greater than 1. No changes. Next candidate, W.
Professor, from V to Z, how is it 4Y?
Sorry, from V to
Z.
U to Z.
No, in the step number 3.
Okay. Why is it 4?
Yeah, 4Y.
Who is the predecessor?
If in N prime we end up at V, right?
No. You asked about this step, right?
Yes.
It is 4Y because we made no changes. The thing is, are V and Z neighbors?
No.
So there will be no change after considering V.
Okay. Okay.
Okay?
Okay.
You will consider only the neighbors of V.
Okay. Got it.
And those neighbors that are not sort of on this, if U is also a neighbor of V, right? But it
Yes.
is already on this path, so you will not consider U.
Yes.
Last step, at W, we have three neighbors of W. You cannot consider Y because we already found the best path to Y when we made it part of this link. Can you find a better path to Z? What is cost to W? 1, 2, 3. Through W, we can reach Z at 3 plus 8. 8. The current best path to Z has a cost of 4. No changes. And now we will say our algorithm has converged. This last node, you will add the last node, okay, and there won't be any computations. What did we get at the end? Once this algorithm completes its execution, whenever we moved a node to n prime, we added an arrow like this. When we added x in n prime, we added this. When we added y, we added this. At the end, what will you get? You will get a tree rooted at the starting node. And basically, you are getting a rooted tree containing shortest paths from U to all other nodes in the graph. I repeat, this is the shortest path tree from the starting node to all of the other nodes. It does not mean that the shortest path from W to U is this one. No, that will be a different story. Okay. Last point. Every router is going to compute the same thing. So every router will choose itself as the starting node and execute this algorithm for itself. And at the end, we will get shortest paths. Okay. What will be the forwarding table? Something like this. This is the forwarding table for starting node U. Destination V is reachable. Outgoing link is UV. So whenever U receives a packet for destination V, it will simply give it to V. X is a direct neighbor and it is reachable. So this link. Carefully look now. Y is added. And if U receives a packet for destination IPY, the packet should go on link UX. So it will simply forward the packet here. Destination W is reachable via the same next hop X. Okay, so this is basically a forwarding table that will be computed once the execution of this routing algorithm concludes. Any questions here? I'm done with this part. So I have added another example. So try to understand the first one, try to manually solve it, or rather understand it, then come on this slide. This is a different graph. Manually solve it yourself on a piece of paper and then compare your answer with this example. Okay. The next class of algorithms is distance vectors. Okay, distance vector routing, slightly different. This one is called link state. Right? Link state means every router shares its link state advertisement, basically information about the connected nodes with everyone in the network. Okay. Distance vector is entirely different. In distance vector routing, let's say the network has just been initialized. I need a good example. I will solve that example in the class or in the coming lab. So I think we can stop here because we did not take break. Let me introduce the topic first. Yes. So let's assume the network has just been initialized, the routers are there, and they have yet to discover anything. Okay. So initially, Z knows no one. Okay. It will announce itself to its neighbors. Okay. So W will discover there is a neighbor Z reachable at a cost of 5, and W will add an entry in its forwarding table. I can reach Z at a cost of 5. Okay. And obviously it will add the next hop node, which is Z directly. Okay. So if W wants to send packet to Z, give it directly to Z. Similarly, okay, that's all. Okay. Now W will generate a distance vector algorithm. Basically, distance vector means every router will update or share its complete routing table with others. W will say, I can reach a destination Z at a cost of 5. And who generated this packet? W, right? And W will share it with its neighbors. Let's say Y. Okay. When Y receives it, Y will do two things. Y will add a new destination W, reachable at a cost of 1. Y will also add another destination 0. Guys, I'm assuming Z has not yet announced anything here. Right? So Y is going to add another destination Z, reachable at a cost of 1 plus 5, 6. And obviously, Y will say next hop to reach Z is W. And Y will update or share this complete routing table with its neighbors one by one. If you see the difference, in the previous algorithm, every node was in one go sharing its own ID and its neighboring IDs to everyone in the network. In distance vector routing, every router, whenever it gets a new update, it finds something new, it updates its routing table and shares the complete routing table with others. The problem, this algorithm is slow. You, on the other end of the network, will get an update much later because Y will learn whatever it learns, update its routing table with X. X will update all its entries, share its updated U. So you will probably get routes to one part of the network from this part. You will learn about the other part from another part. So slowly and gradually, distance vector is going to enable every router to discover routes. And solution is same. At the end, in both the algorithms, every router will be able to route traffic to any destination based on the shortest paths. That's a good thing. The bad thing is this algorithm is slow and has some issues. Let's cover them in the class when we meet. So in the coming class, I will quickly cover distance vector routing. It's also part of the next lab. Then I will quickly conclude and discuss the structure of IPv4 packet. We will also capture it in Wireshark, and we will be done with this chapter. Okay. Next, we will focus on the last chapter, which is data link layer services. And inshallah, we will be able to cover it in 1.5 lecture only. Okay, there aren't many topics. We will cover a part of it in the lecture and a part of it in the lab. That's all from my side. Please, over to you. If you have any questions, please let me know. Thank you. Bye, everyone.
Thank you, Professor.
Thank you. By the way, I did not check how many students were available throughout the session. Thank you.
Thank you, Professor.
Professor, hi.
Hi.
I arrived a little bit late. Would you mind going over quickly on the points you covered before the longest
The longest prefix match. Okay. I'll pick
yes.
it. Others can leave if they want to. Okay.
Thank you.
Give me a second. I want to first download the attendance list.
Yes, of course.
Oh.
Is there attendance, Professor?
No, I can download a list here, so I'm downloading it here. I know it's possible. So
Okay. So we can leave, right?
yes, you can leave. I'm just downloading that list.
Okay, thank you, Professor.
Okay, let me share my screen back. Is my screen visible? Ahmed.
Yes. It is.
Ah, that was the previous.
Yeah, it was the previous PowerPoint. Yeah.
Hassan, chapter 7, whatever we covered till today, is included in the quiz. I will send an email in half an hour. Don't worry.
Covered a lot.
Already shared. Is it not visible or Moodle? Please check. If there is any problem, please let me know now. I shared it yesterday.
Yes, before this, please.
This one, right?
Yes, before this. I was wondering if you could quickly just go over these points.
Ah, these points. Okay. That will take some time, by the way. I recorded the session.
Oh, you did?
Yeah, I recorded everything. I will share the link over Moodle and go through it.
Okay, thank you so much.
I don't mind going through it again, but it will take like 20-30 minutes. We spent quite a lot of time.
If I don't mind,
Quickly.
to be honest.
Quickly record the watch the recording, and if you have any concerns, meet me on Monday.
Okay, sure. Thank you so
Okay.
much.
Okay. No, I thought you had a specific question about something.
No, I just arrived late because I forgot it starts at 1.
Okay, no. In fact, first I taught how to supernet multiple subnets,
Okay.
for which I covered a different file. It was a Word file already uploaded on Moodle.
Okay, got it.
And then I covered these points. Basically, these are the rules that will tell you when supernetting cannot be done.
Okay, got it.
So that was like almost 30 minutes of discussion. Okay.
Hmm.
Great. Hassan, were you able to see the project's description?
Okay, thank you, Professor. Have a good day.
Thank you. Let me check if there is any problem. Sometimes the
Recording.
assignment or a file is marked as hidden. So I will check it now and I will correct it. Okay. And I will also send an email to all of you. Okay, let me check. I will send an email, and after my email, if you can still not see, let me know. Thank you, everyone. Thank you. Bye.
Goodbye.
You're welcome.